engineered spin-orbit interactions in lanthanum aluminate strontium titanate based 1D serpentine electron waveguides. What does this all mean? You're watching 11 Levels. Note that this is not based on the video series 5 Levels by Wired.com. Okay, maybe just a little bit. Let's get started. Level 1. So I'm going to talk about the title of this paper and each of the phrases and words that you see here. So let me begin with the word engineered. What do we mean by this? Well, engineering you can think of as the construction or creation of something that is based on principles or understanding that we have about our world and our universe. So if you were to engineer a bridge, you're designing and building a bridge based on principles of mechanics, and the bridge would have some function or utility. So we're going to be designing structures like the ones that you see down here. These are very, very tiny wires, and they're going to have properties that we are going to be creating using the choice of the pattern that we are going to be putting in these wires. So the material that we use is like an Etch-a-Sketch, but it's fundamentally different in terms of how it operates and what it's being controlled and how big it is. So an Etch-a-Sketch is an enclosure where you have aluminum powder, and the aluminum powder sticks inside sticks to the plastic sheet that is on the front surface here, and the bright regions are the places where the aluminum powder is present. So it's shiny, and well, each little piece is diffuse, so it basically when light reflects off of it, it produces a bright region. And you can scrape off the aluminum powder with a stylus that is on the other side of this screen, and it's pointed at the opposite side, and you can move the stylus in the horizontal and vertical directions. And if you're talented, I did not make this drawing, but if you're talented, then you can create patterns of remarkable complexity. And this is a rewritable interface that can be turned upside down, and you can put the aluminum powder back on and start with a fresh canvas. So we're working with a material that has properties very much like the Etch-a-Sketch. So we're taking a very thin layer of this material, lanthanum aluminate, and it's so thin that there are only a few atomic layers. So each of these circles that you see here represent individual atoms, and this is only less than 2 nanometers thick, so 2 billionths of 1 meter in thickness. And then the rest of the material is strontium titanate. So both of these are insulating materials, so they don't conduct electricity. But when you put them together, the interface between them in the strontium titanate region can be made conducting. And in fact, it can be switched back and forth between conducting and insulating behavior, just like any point on this surface can be made bright or dark by the presence of or absence of aluminum stuck to the inside of the plastic sheet here. So we're going to use this ability to create nanostructures, nanowires, and electron waveguides. For a long time, we have been working with these straight electron waveguides. These are relatively short segments of wires that are about 10 nanometers wide and several hundred nanometers long, and they have properties which are very interesting in and of themselves. What we have done in this paper is changed the straight segment here and made it serpentine. So we're now forcing the electrons to wiggle back and forth as they travel from one side to the other. And so we want to understand what is the effect that wiggling has on the electronic properties. So So it turns out that it allows for two properties of the electrons to be coupled together. So here what you see is a model of an atom where you have the positive charge in the center, and then you have electrons that are orbiting the atom. Now this orbital motion, this is a type of motion, so when the charge moves, it actually can generate a magnetic field. But the electron itself has its own spin magnetic field, and there's a coupling between the spin of the electron and its orbital motion, and this is known as a spin-orbit interaction. So this type of spin-orbit interaction can be engineered. You can see that the electrons are moving in a curved region, so they're moving in a circle. If you look over here, this wiggling is actually part of a circle. It's like a semicircle on the top and then a semicircle on the bottom. This wiggling motion is similar to the type of wiggles that electrons have when they orbit in a nucleus. And so we are able to engineer these spin-orbit interactions by creating the wiggling pattern for the electrons to travel. All right, level 10. When we think about the way that electrons normally conduct in metals, most materials, we realize that they behave according to Ohm's law. So Ohm's law is a relationship between a voltage that you might apply across a material that has a resistance given by this quantity R, such that the current that flows through this material times the resistance R is equal to V. On a microscopic or more microscopic level, we know that the electrons are actually moving and scattering. They're scattering off of impurities, off of vibrations in the material, and this leads to energy being dissipated, and it leads to this actually what is the same relationship that you see over here, but expressed in a different way. So G is 1 over R. This is the conductance, and it's given by the current that flows divided by the voltage. So for a given voltage, higher current flow would correspond to higher conductance. So as I said, most materials behave like this, but there are a class of materials where the electrons actually move without scattering, or essentially without scattering. And these are known as ballistic conductors. So you might think of them as electrons like cars moving in the lanes of a highway. And so in this case, the conductance, G, is given by very fundamental parameters of nature. So the E is the electron charge, so the electron charge squared divided by Planck's constant. This quantity here has dimensions of conductance, and the conductance of a ballistic wire or conductor would be given in terms of this quantum of conductance, E squared over H, with a multiplicative factor n, where n is the number of channels that the electrons can flow in. So these are meant to be distinct channels. They don't have to be channels that are displaced like in a highway. This is more of a metaphor. The electrons are actually overlapping and coexisting in space, but they look different, and they are distinct from one another. They have to be, because electrons cannot be in the same, two electrons cannot be in the same state at the same time. So this map that you see here is an experimentally measured map of the ways in which electrons can flow in these straight or unmodulated electron waveguides. So each one of these dark regions here represents a state where we have either 0 lanes or 1 lane or 2 lanes of this electron highway. So over here at the bottom, the waveguide is insulating, so the vertical axis is allowing us to change what's called the chemical potential in the wire, which allows us to put more and more electrons inside of the wire. And as we do that, we eventually get to this plateau here, where the conductance is given by E squared over h times 1. And then if we keep going up, we have E squared over h times 2, times 3, and so forth. So each time we cross one of these bright bands, we are introducing a new way for electrons to travel, a new lane in this waveguide highway. So the question is, what happens when you take this waveguide and you make it wiggle? You make it serpentine. Well, it turns out, now this is a different color because this is a different paper. We chose a different color scheme, but it's the same information that we're representing, where instead now of the lowest region here being at the smallest value of the applied magnetic field, so we're applying a magnetic field in this experiment, we find that the minimum is actually occurring at a finite value of the magnetic field. So it's as if the externally applied magnetic field is competing with an internal magnetic field, which we believe is arising from this spin-orbit interaction. So there are other features as well that appear, but this is one of the main effects that we observe as a consequence of this, this type of wiggling motion. So we're able to create these new interactions by changing the shape of these wires. All right, level 11. So we're describing electron waveguides, and they have a few parameters like the length and the width and so forth. There's a side gate. All of these can be created on demand using this conductive atomic force microscope lithography technique. So this is one particular structure that we can create, and we can erase this and create another structure and so forth. So the way that we often describe the electron waveguides is as follows. We imagine that the waveguide can have several electronic bands or subbands. These are the lanes of the highway, if you will. We represent them as electronic states that are allowed, and they are allowed for different values of the momentum of these electrons, which is given by this number k sub x. So each one of these distinct subbands represents a different lane or a mode for the electrons to travel inside of this quantum wire, and we can allow fewer or more of these subbands to be occupied by adjusting the gate voltage on at this side gate. So here in this representation, there's only a single electronic subband allowed, and we would expect the conductance here to be given by E squared over h times 1. But in the description or depiction below, we now are occupying 3 distinct electronic subbands. We've changed the chemical potential and put more electrons in the quantum wire, and now there are 3 occupied subbands, and so the conductance here would be given by 3 E squared over h. And so we expect that as we change this gate voltage, we change the chemical potential energy, we would see steps in the conductance, with the plateaus being given by integer values of the conductance quantum. So the last thing is that the bottoms of these subbands themselves can be adjusted by coupling to an external magnetic field. And so if we track the bottom of these subbands, they can move up or move down in energy depending on the spin and orbital degrees of freedom. So we can describe this quantum mechanically by writing down a Hamiltonian for a single particle that exists in the quantum wire. These 3 terms represent the kinetic energy of the particle in the propagation direction, x, as well as the 2 transverse directions, y and z. So these would provide confinement energy, and this would give you kinetic energy along the direction of the magnetic field. Then we know that the electrons are trapped inside of a potential well, and we model this by a parabola. So that's why we have the y squared in the lateral direction. It's actually a half parabola in the z direction. So The last thing is that we have a magnetic field, which we know couples to the spin degree of freedom of the electrons, and it also couples to the orbital through the vector potential. So we can take this equation and use separation of variables and solve for the eigenstates and eigenvalues, eigenenergies. And what you're seeing here on the upper right is a representation of the cross-section of the wave functions. If the wire were pointing into the plane, these would be the lowest wave energy eigenstate projected onto the two cross-sectional dimensions, the y and the z-axis. So this is the extent of the wave function, and then this is the first lateral excited state, the second lateral excited state, the first vertical excited state. These numbers here represent the number of nodes or zero crossings of the electron wave function, and there are as many for the spin up state as the spin down state. So these are the eigenstates, and then they're multiplied by this e to the I kx, for the motion along the wire itself. Now the energies of the states are also computed at the same time, and we have an energy which depends on k sub x, but if this term is equal to 0, then we have an energy which depends on the magnetic field, and it depends on the quantum numbers n and m, where n and m are these numbers here. So if we were to plot them for different values of n and m as a function of magnetic field, these would be the values of the energies of these distinct subbands as a function of magnetic field. So it turns out that we have really good agreement with the experimentally measured quantum wires. So this is the bottom is the theory, the modeling, and the top set of curves is the experimental data. So you can see these plateaus where the conductance is given by integer values of e squared over h, 1, 2, 3, and so forth. And the way that we generate the curve on the right is by taking the slope of this curve, the derivative, and plotting it as a bright region, whereas the flat regions are darker regions. This is the color scale. So the idea is that we can essentially identify every one of these subbands with this model, but there are important deviations. But the point is that this is a highly ballistic channel that we're beginning with. We're working with a channel that is a straight electron waveguide. And so now what we're doing is we are modifying the waveguide and making it move side to side, and we want to ask what happens as a result of this change, this perturbation of the straight electron waveguide. So it turns out that there are two things that happen. One, I mentioned a little bit earlier, that you see that there's now an energy minimum happening at a finite magnetic field value. This looks like there are two crossing parabolas that are shifted from one another. We believe that this is due to the effective magnetic fields that are produced through the spin-orbit interaction that has been engineered. But this is not the only thing that we observed. We also found some very surprising, or initially surprising, features that you would not expect from the ballistic electron waveguide picture. So what you see here are a set of plateaus which are magnetically tunable, and they occur at fractions of the conductance quantum value. So here, this dashed line here represents the quantized value, which we observe at sufficiently high magnetic fields. But eventually, but there is a point where we start to see these extra plateaus happening at a fractional value. So this is a really remarkable emergent feature that is coming about, we believe, due to interactions between the electrons combined with the spin orbit with the spin orbit interaction that is being engineered. So these emergent phases are quite interesting and are not described using the single electron picture. So this is really revealing some features of one-dimensional transport that makes 1D physics very different from 2D and 3D. So this is one of the main findings of our publication. So the work that I'm describing here was part of PhD work of Macon Kirkendall, Macon Bridgman, who received her PhD in 2019, and also this work is done in collaboration with Professor Patrick Irvin at the University of Pittsburgh. The two then PhD students also involved in the work, Jianan Li and Mengchen Huang, they played an important role in the development of the work that you saw today. So I'd also like to acknowledge long-time collaboration, very important, with Professor Changbom Ohm at the University of Wisconsin-Madison and his group of postdocs, Hyungwoo Lee, Jungwoo Lee, and Kitai Ohm, who have produced the wonderful lanthanum aluminate strontium titanate heterostructures that made this work possible. So I'd also like to acknowledge support for this research from the National Science Foundation, as well as from Vannevar Bush Faculty Fellowship.